So I'm going to be doing two lessons today. So the first one is on absolute ages. So the lesson we just did was on relative ages. So I want to make sure you know the difference between the two. So absolute ages is when you find an age in a specific number of years, and we're going to use atoms to do that. So I'll explain the atoms part coming up, but I want to make sure you understand what the age in years mean. So I'm going back to my little image here with the rocks that I did with relative age. So in absolute, if the one rock says, "Hey, how old are you?" The other rock's going to say, "I'm 75,000 years old." He's going to give an exact number. Whereas in relative age, the other rock did not, I know this is kind of silly, but to help you understand, the other rock did not give an exact number. He just said, "I'm older than you." So relative age, we looked at older versus younger. Whereas now that we're getting into absolute age, this is a specific number and actually uses some chemistry to do it. So I was excited to get to this lesson because I get to teach a little bit of chemistry, which is one of my favorite sciences. So you won't need to write anything down on this slide unless you've never learned it before. If you're familiar with an atom, you probably don't need to write this down. I'm just not sure what you've had before. So in an atom, which is the smallest part of an element, so in the very center, it's called the nucleus. So you have these orange plus signs. Those are called protons. They have a positive charge, which is why there's a plus sign. These green are neutrons, and neutron, they're neutral. They're not positive or negative. Then you have these orbits around the outside that are not in the nucleus that have electrons. So that's a purplish color. And there's a minus sign. Those are negatively charged. Okay. So it's just kind of a little background for you. Still going into some background here. That's the chemistry background. So there's something called isotopes that show up in this absolute aging of rocks. So an isotope is an element with the same number of protons but different number of neutrons. So going back to this one, the pluses in the nucleus, the protons would be the same, but different number of neutrons. So if you look at the picture, I have hydrogen here. So an element, if you ever heard the periodic table of elements, hydrogen, helium, oxygen, carbon are some really common ones. They are going to have the same number of protons, no matter what. Hydrogen always has one proton. So you'll see all three of these isotopes, one proton, one proton, one proton. However, the neutrons, which are those neutral ones in the nucleus that are green in that picture, are going to be different. This one doesn't have any neutrons. This one has one, this one has two. They're all still hydrogen because they have one proton, but an isotope has a different number of neutrons. So what does this have to do with rocks? I'm still not even there yet, getting to the rocks. I'm going to get there. So we're talking about radioactive decay, which helps us to figure out how old rocks are. So radioactive decay is breaking down. So radioactive decay is when atoms of one element break down to form other isotopes. So there's two types, alpha and beta. So one thing I want to go over first is that isotope that you start with, they call it the parent, which to me makes sense. And then it's going to break down into a daughter. So when it's decaying or breaking down, that's when you get to the daughter. So just two terms, they make sense to me. Parent is the isotope you start with. As it breaks down, they call it the daughter. So in an alpha radioactive decay, it's going to break down into the daughter, which has two protons and two neutrons, but it's also going to have this alpha particle emitted that comes out. So in alpha, you go from parent to daughter, which is all of them that decay, and then you have alpha that come off. Whereas the beta, still going from parent to daughter as you're decaying, but instead of having an alpha particle come off, you have an electron that comes off as a beta. So that's why it's called beta, because the electron comes off. So what does this have to do with rocks? We're getting there. Not there yet. We're going to get there. So there's something called half-life. Still chemistry here. Half-life is the time it takes for half the atoms of an isotope to decay. So we still have isotopes. That's why I had to teach you what an isotope is. Now we're decaying the isotopes. So this image down here is actually from Edgenuity. I thought it was pretty good, so I used it. So when there's no half-life, the original parent would be 100% parent. That's before you do anything to the isotope. Then after one half-life, it's the time it takes for half of it to decay. You end up with 50% parent, 50% daughter, half and half. Then once a second half-life happens, then it cuts it in half again. So you end up with 75% daughter and only 25% parent. The darker color, the black, is the parent. Another half-life cuts it in half again. So you're only left with 1/8 of the parent. and now you're at 7/8 daughter, and going on and on and on. And eventually, after many, many, many half-lives, half and half and half and half, eventually it's going to be completely daughter. The parent will no longer be there. Here's another colored one for you. So the parent is that maroon color. So at 0 half-lives, it's all parent. 1/2 half-life, it's half and half. And then 2 half-lives, you'll kind of notice again, it was 3/4 and 1/4. So there's a lot more daughter. What does this have to do with rocks? Here we go. We're getting there. So with rocks, we use radiometric dating, and this is for absolute age. So this is not relative comparing, I'm older, younger. This is getting an actual number. So this is where all that chemistry led to right here. So radiometric data is looking at the ratio of parent to daughter. So the ratio here would be 1:1. The ratio here would be 3:1, 7:1. So that's the ratio looking at parent and daughter, the amount. And that helps us to date. Then there's one specific type they talked about, radiocarbon dating. This specifically uses the isotope called carbon-14. This one is great. The only one thing it can't do is it can't do ancient fossils. So it has to be 75,000 years old is the farthest it can go. Anything older than that, you can't use carbon. So you kind of see in this picture, you can see the atoms at the bottom. You can see less and less parent. And then they have the years, the absolute years. So they throw this in really, really quickly. Uniformitarianism. Whew, that's a mouthful. So this is just saying that Earth's processes today are similar to those of the past. So it's just kind of learning from what happened before that leads up to something in today and helps us to learn. So this is the second lesson. Luckily, it's a lot shorter than that first one. So it's geologic time. So this is when we look at all of Earth's history, 4.5 billion years, and dividing it up into smaller units. So we use that how the life forms change, specifically animals, but plants as well. How did they change and divide it up? It helps us look at history a little easier. And by life forms, I mean organisms, plants, and animals. So there are divisions. Eons are the longest divisions. So they're big chunks of time. Eras are the next biggest, I guess, and they're going to be major worldwide changes. And then the period, nothing really noteworthy about that. It's just the next largest or second smallest. And then the epoch are the very, very small divisions. So if you want to look at this one, the Earth is 4.5 billion years old. And this is kind of divided up. You don't have to memorize all of this, but you'll see eon, era, period, and epoch. And the longest time period is actually this reddish pink down here. It's called Precambrian era. And in this graphic, it doesn't really look like it, but this is actually the most amount of time. If you look at these numbers at the side, the most amount of our history was Precambrian. There wasn't a lot of life forms, so they don't divide it up like they do up here. But really, if you did this to scale, almost all of this should be red. So just kind of keep that in mind. Then there's moving into how the life forms changed. So first they throw in the vocab word species. So a species are organisms that reproduce with only other members. So dogs only reproduce with dogs. Most species do this. A dog's not going to reproduce with anything else. There's some species that do that, but most do not. All species won't. So then there's two types of ways that these change. So natural selection, natural meaning in nature, has no help. So natural selection is the most well-suited for the environment will reproduce. So the least well-suited will die off. So for example, they always do the giraffe. So at some point, giraffes did not have necks that long. And then there was probably a drought, and the ones that lived were the ones who had longer necks because they could get the leaves that weren't dead on trees and eat them. Whereas if you didn't have a long neck, you couldn't get any food, so you died. So then over years and years and years, again, the ones with the longest necks survived. So then they made more babies with long necks. And then their strongest with the long, and you can see on and on and on and on. Eventually we have giraffes with really long necks. Then there's also artificial selection. This is artificial because it does not happen on its own in nature. Humans do this. The most common example in our lives would be dog breeding. So this is putting dogs together to get the fastest or the most attractive or the best ears, or a non-shedding dog with something else. Labradoodles they put together. So this is artificial. They talk about trilobites, which trilobites are really helpful in terms of some of this dating and looking at changes. So a trilobite is three-lobed and it has an exoskeleton. That has never changed. It's always three-lobed. We use this as an index fossil, which you learned about last week, and it's going to help track changes that have occurred in the environment and the survival of the trilobites. Some of the changes they look through over time are in the trilobite's eyes and the different body parts. So then what causes these changes that trilobites have gone through? You already learned about this. I'm not going to talk much about it. Plate tectonics. We started at Pangea. As those plates shifted and moved out, it's going to cause a lot of changes. And the new part is these fossils helped us to figure out those changes. And that is the end of that lesson.